Hello, this is the Introduction to Organic Chemistry tutorial presented by the SHRTB with reference Cambridge International Areas by Laurie Ryan and Roger Norris. So this is the Introduction to Organic Chemistry, and in this introduction we're going to start the learning outcome. So you need to know how to interpret and name the use general, structural and displace and skeletal formulae of different molecules in organic chemistry. We have understand and use the following terminology: functional group, homolytic and electrolytic fission, free radical, initiation, propagation, and then termination, nucleophilic, electrophile, addition, substitution, elimination, hydrolysis and condensation, oxidation and reduction, and describe and explain the shape of bond angle in ethane molecules in terms of their pi, and predict the shape that they are going to have a different bond angle related to the molecule. And then the last one is to describe and explain the different types of structural and stereoisomerism. So we start from here. So, introduction to organic chemistry. The first thing in organic chemistry is to point out the fact that an organic chemistry is the study of carbon-containing compound, with the exception of the metallic carbides, the oxides of carbon, and the carbonates of carbon. So the study of carbon-containing compound, with the exception of metallic carbides and carbonates and oxides of carbon. Now, the next question to ask ourselves is, why is carbon having a chemistry on itself and not other elements? So we know that for other elements, we are studying elements mostly in groups, but carbon is studied in a chemistry for itself. So why is this carbon? What are the specific properties of carbon for it to have a chemistry on itself? The first point is that carbon is capable of forming 4 covalent bonding with itself and other molecules. That is first point. Second point, carbon is capable of forming strong single, double and triple covalent bonds with other molecules, strong stable bonds. And the third one is that carbon is very small in size, and then it is capable of entering into the electronic space of the other atoms, so making the bond to be stronger. And then the last one is that carbon is capable of catenation. So what is catenation? Catenation refers to the ability of an element to bond to itself, forming stable long straight chain. The ability of an element to form stable long straight chain with itself. So that is catenation. So now we need to know that in organic chemistry, since organic chemistry involves very long molecules, we need to know that there is quite a good representation that we need to use for this organic molecule. Like this representation is called the modeling, the molecular model. So these are the molecular model that you can visualize. So example of variety of hydrocarbon. So we have the diagram A here. These are different hydrocarbon from A to C. This is one form of modeling, just to show the representation of atom, and this is another form of modeling where you use small hands in order to show bondings. So these are the different points. So now these are the different colors that you are going to visualize for each of the molecules. White is used for hydrogen, dark gray is used for carbon, red is used for oxygen, blue is used for nitrogen, yellow green is used for fluorine, green is used for chlorine, and all the others are here. Now, the next point to find out is what's the definition of empirical formula. The empirical formula is the simplest formula of an organic molecule. The empirical formula is the simplest formula of a molecule. What do I mean by that? If you have a molecule like ethane, which is C2H6, so the simplest formula of C2H6 is going to be C3. That is, there's a factor of 2 which is both found on C2, and there's a factor of 2 found also on H6. So when you divide all through by 2, you are going to have CH3. So the empirical formula of that ethane is going to be CH3. So the simplest formula of an organic compound. Now let's see the next one, molecular formula. What is molecular formula? The molecular formula refers to the complete formula of that compound. So in this case, ethane is going to have 2 carbon atoms, and also going to have 2 carbon atoms, and is going to have again 6 hydrogen atoms. That's the case of ethane. Now the next one is a structural formula. So in this diagram you can visualize a structural formula in the model of the molecules, a molecular model. So now the structural formula is a formula that is going to represent the structure of the molecule. Molecular formula was just representing the number of atoms found in that per element, the number of atoms of that element found in a molecule. But the structural formula is representing the actual structure that those atoms are displaced in space of the molecule. So the next one, so here you can see that it's displaced in space. Then the next one, you have the skeletal formula. Like this example here is a structural formula of propane. You have CH double bond, CH here. So this is propane. So now we are going to see the naming of organic molecules in order for you to know how we can easily name this molecule later. So now the next point to visualize is going to be the skeletal formula. The skeletal formula is a formula which is going to have the representation of the molecule without the representation of molecule without any element symbol. So in this formula you see that there is no element symbol, but there is only bonds. So you need to know that when you draw like this, it's a representation of propane. Here the C is not written, but when you see bonding, so I know that here is going to be a double bond. It's just to show that which bond is prevalent in that molecule. So this is going to show you a double bond, this is going to show you a single bond. So you know that you need to know that at this term that there is going to be carbon, and that carbon is going to be bonded to 3 other hydrogen atoms which are not placed. So at each terminal, at each point of the bonding, you have a CH3, or you have a CH2, or you have a CH, depending on which type of bonding you have. Then the next one is now the structural formula. The structural formula of butane 2-ol, and the skeletal formula of butane 2-ol. So now we also have the zigzag formula. The zigzag formula is the formula mostly used in the CRAM model. So this formula that you see here is a formula mostly used in the CRAM model, and this formula is there to show you the 3-dimensional view of an element. So from here you see that when you draw this structural formula, it displays only the molecule in a 2 dimension, that is on a plain sheet of paper. But this zigzag formula is going to represent the 3-dimensional view of this atom. So example, when you see this hydrogen here means that it is inside the paper. So when you see this arrow, the dark arrow here means that it is entering inside the paper. It is this dark arrow, it means that hydrogen is entering inside the paper. And when you see this stroke arrow here, it means that this stroke arrow here means that hydrogen is entering inside the paper, and this dark arrow here means that hydrogen is coming out of the paper. So the molecule attached to it are representing the 3-dimensional view of this formula called a zigzag formula. So now we have this formula which are attack the combined formula of all this one. We have the structural formula, we have the zigzag formula, we have everything, the skeletal formula, and all the like. So now let's visualize the main molecules which are found in organic chemistry. In organic chemistry, these are all the molecules that we're going to study. We are going to start with alkenes. In alkenes, we are going to start with alkenes and alkenes, or hydrocarbons. So we need to know that alkenes have a general formula of CnH2n. Example, we have ethane, and that's the structural formula. We have arenes. The arenes have C6H5 bonded to something. Example is benzene, and it's written as that structural formula. Then we have the halogenoalkanes, which have CnH2n plus 1. This is an alkyl group, and it's going to attach to an X, which is a halide. Example, chloromethane, and the structural formula for that is here. We have alcohol. The general formula is CnH2n plus 1. That's an alkyl group plus the OH. Example is methanol, and we have CH3OH. We have aldehyde. The general functional group is going to be D, CH double bond O, and then H for aldehyde. And then you have CN, H2N plus 1 CHO, and this one here is going to be the alkyl group attached to this molecule. Example is ethanol. You have CH3CHO. The next one is going to be a ketone. The ketone here, you have this molecule as such here, double bond O, you have CH and other. You have CN, H2N plus 1, and then you have CO, you have CM, H2M plus 1. So these are ketone group. You need to know that there is an alkyl group here, is an alkyl group here. This is why you have two alkyl groups at each position of the CO, and this CO is called the carbonyl functional group. An example here is going to be propanol, and you have CH3 alkyl group 1, a methyl group here, we have a methyl group here, and the middle you have CO. Then the next one you have carboxylic acid functional group C double bond O, you have single bond OH. You have an alkyl group CN, H2N plus 1, COOH, ethanoic acid, and this is the formula here. Then we have an ester which have an alkyl group attached here. We have a C double bond O, a O, and an alkyl group. So that's why you have this alkyl group formula. You have C double bond O, and then you have another alkyl group formula. Example is ethyl ethanoate, and this is a form of ethyl ethanoate. And then we have amines. Amines, you have an alkyl group attached to the NH2 group of that amine. An example is methylamine, and this methylamine formula is here. And the last one is nitrite. Nitrite have an alkyl group attached to the CN functional group of nitrite. An example is ethanonitrite, and we have the formula of ethanonitrite here, CnH3CN as such. So now let's see now the definition of a functional group. What is a functional group? You have been hearing the word functional group, but the functional group is actually defined as a group of atoms or bonds. It can be defined as a group of atoms or a single atom. It is defined as a group of atom or a single atom or bonds that is going to determine the specific chemical property of a certain group of organic compounds. So that's the definition of functional group. So now a functional group usually is usually belonging to a particular homologous series. A functional group belongs to a particular homologous series. And then the next thing is, what is a homologous series? A homologous series is a group of compounds which have a similar functional group and whose next element or the preceding element is going to differ from the former element by a CH2 group. So we take an example of the alkene functional group. In the alkene functional group, you have the CH4. We need to know that the functional group in alkene is going to be only the H2. So we need to know that in this case, you see that you have CH4 here, and then you have C2H6. The difference between CH2, C2H6 and CH4 is going to be a CH2, and this CH2 is what is the peculiarity of a homologous series. A homologous series have the same functional group, and then the next element differ from the preceding element by a CH2 group. So this is what we have to point. So we need to know how to give some names to this. So when you see only one carbon atom, you call it mate. When you see two carbon atoms, you call it 8. When you see 3 prop, 4 but, 5 pens, 6 hex, 7 hep, 8 oct, 9 non, and 10 det. So now, depending on the functional group, since this functional group is alkene functional group, I'm going to add an "ene" at the end. So I'm going to have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. So these are the different things in visualize here. We need to know again what is meant by a branch chain and how to name it. So this is a branch chain. A branch chain, when you want to name this type of molecule which are branch chain, you need to take first the longest chain involved here. The longest chain in this case is going to be 1. You can count the number of atoms in relation to all the chain. This is 1, 2, 3, for 5 carbon atom in this direction, and in this direction you have 1 2 3 carbon atoms. So this is the longest chain compared to this one. So this is a side chain. Since it's a side chain, I'm going to call it first pentane, because the longest chain has 5 carbon atom, and then I'm going to count the carbon atom which has this methyl group, because CH3 is an alkyl group called methyl. I'm going to call it 2-methyl pentane. So now let's name this other molecule. In order to name this molecule, I'm going to take the direction of the largest molecule. Example, I'm going to start this direction. 1 2 3 is not long. 1 2 3 is not long. 1 2 3 4 is not long. 1 2 3 4 5 is long, but let me count again another direction. This is 1 2 3 4 5 still. 1 2 3 4 5. So the longest chain is going to be a methyl, is going to be pentane. The longest chain is going to be C5. But now we are going to count the longest chain so as to reduce the number of side chains. So that's the point. You're going to count the longest chain so as to reduce the number of side chains. So I'm going to count in this direction. So I'm going to have a 2, so this is 2 and 2. I'm going to have 2 2 and then 3. So I'm going to have 2 2 3 trimethyl pentane. So that's the name of this molecule. So now we have already named, we can now display. This is a displayed formula of the skeletal protein of this benzene, and this is the skeletal formula of benzene. So now we have different names. We need to know that this carbon atom here is going to be called carbon atom number 1, but depending on where you start your counting, here is going to be carbon atom number 1 at this other position. So this is the ortho position, this is the para position, this position here is the ortho position here, this is the meta position, this is the para position. So this one is going to control, you are going to have the 2 here, so 1 2 dimethyl benzene, or you can still call it orthomethyl benzene. So all that's the name. So this here is going to be called 1,4 dimethyl benzene. So these are the different names we are going to visualize. Then the next thing to visualize in organic in the introduction of organic chemistry are going to be sigma and the pi bonds. Okay, before we move on to sigma and pi bonds, I want also have a general introduction in the bonding involving with carbon atom. Point number 1, if you visualize the electronic structure of carbon atom, we are going to visualize that carbon atom has an atomic number of 6, so 6 electrons are going to be found in all its shells. So if I do the SPDF electronic configuration of this carbon atom, I'm going to visualize that it's going to be 1s2, 2s, I'm going to visualize it's going to be 1s2, 2s2, 2p2. But now you realize that if I draw the electron in box configuration, electron in box notation of this electronic configuration, you're going to visualize that there is going to be only 2 unpaired electrons in the 2p orbitals. But the question that I want to ask myself, and I want to ask all the audience which are hearing this video, is why is it that carbon is doing a 4 covalent bonding while there are only 2 unpaired electrons in the 2p orbitals? So the answer is answered by some others, while others don't prefer answering that question in this method. But I prefer one main answer to this question, and this question, the answer is going to be hybridization. And now, what is hybridization? Hybridization is defined as the mixing of similar orbitals, example the s and the p orbitals, with the rise of electron from a lower energy level to higher energy level, producing new equivalent orbitals with the same energy. That's hybridization. So now hybridization can be sp3, that is one s orbital is going to hybridize with 3 p's orbital. So example sp3 hybridization. Another hybridization could be sp2, where one s orbital is going to hybridize with 2p orbital, and you have sp hybridization where one s orbital is going to hybridize with only 1p orbital. And the p, you must put in mind that 1p, the p orbital which must be hybridized is a px orbital. So these are the points that you need to visualize. So now let's start. We have different methods of hybridization we have different methods of formation of sigma bonds. the first point is that a sigma bond is going to be formed when one s orbital is going to bind with another s orbital. That's the first point. The second point is when one px orbital is going to bind with another s orbital. That's the second point. The third point is when two hybrid orbitals are binding, and the fourth point is when one s orbital bind with a hybridized orbital, or a hybrid orbital. So these are the points for the formation of sigma bonds. And now you need to know that examples of sigma bonds, you are only going to see sigma bonds in cases of alkanes, because alkanes have the hybridization of all their orbitals. So since there's hybridization of all their orbitals, all of them are going to form sigma bonds when they are going to bind with the corresponding others. But now we need to know that in molecules like alkene and alkyne, we need to know that there is pi bond. And now the question is, how is pi bond formed? Pi bond is formed when you have two py orbital binding to work together, or you have two p z orbitals binding together. So the question is, now why is it that alkenes and alkynes have py and pz orbitals which are left free? So this is because we need to know that in alkenes you have sp2 hybridization. So that is the 2s orbital has hybridized or has combined with 2p orbitals, with a 2p orbital. Since they have combined together, there is going to be one p that is going to be left with one electron which is unpaired, and that p orbital which is going to be left is going to be py orbital. So the py orbital of one carbon atom is going to combine with the py orbital of the other carbon atom, producing the pi bond. And this is why this is how pi bonds are produced. So this is why you realize that in cases of ethene, which is an alkene, you realize that the first pi bond is that one of the double bonds is going to be more unstable than the other, and this is because that one double bond is going to be the pi bond. So the pi bond is more unstable than a sigma bond because the bonding electrons are further away from the bonding nuclei. So there is less interaction, electronuclear interaction compared to the sigma bonds, where the bonding electrons are going to be closer to the bonding nuclei. So now let's visualize what is isomerism. So before we visualize what is isomerism, let's define isomerism. Isomerism is defined as the existence of molecules having the same molecular formula but different structures. So now the question is, why is it that they have the different structures? So we are going to answer the question in the different types of isomerism. We have two main types of isomerism called structural isomerism and stereoisomerism. So let's define each of them. Structural isomerism is defined as the existence of two molecules having the same molecular formula but different structure due to different carbon chain and different structural arrangement of the atoms. But now, what is stereoisomerism? Stereoisomerism is the existence of two atoms or the existence of molecules having the same molecular formula but different spatial arrangement of atoms in space, spatial arrangement of atoms in the molecules, different spatial arrangement of atoms in the molecule for stereoisomerism. So now, what are the different types of structural isomerism? For structural isomerism, we have positional isomerism, we have the next one, functional group isomerism, we have chain isomerism, and we have one which was omitted here, tautomerism. So these are the points that we need to visualize here. So we have now, let's start with positional isomerism. So what is positional isomerism? Positional isomerism refers to molecules. So we first have the first one, positional isomerism. So here we have one functional group, and this functional group is we are going to have different the different orientation of the functional group with respect to the chain. Example we have in cases of this molecule here. So this molecule has two bromine functional groups. So these are a halogenoalkane. So you see that this halogenoalkane is going to have the same molecular formula for all of them, and this is the molecular formula. But now these are all the position isomers that you can have. One of the isomers could be like this, another isomer could be like this, another isomer could be like this, and another isomer could be like this. So that it has the same molecule, but it has the same molecular formula, but these are the different structural formula due to the different position of the functional group, and in this case the functional group is the halide. So now let's go now to the next one, which is functional group isomerism. Functional group isomerism, they say have the same molecular formula but different functional group. Example is between an alcohol and an ether. So this example is going to be propan 1-or and methoxyethane. In this case, you see that there's an OH group, but in this case, you have an O binded to alkyl group for methoxyethane. So this is a functional group isomerism, having the same molecular formula but different functional groups. So the next one is going to be chain isomerism. Chain isomerism, in this case, you have the same molecular formula but different carbon skeleton. So in this case, you have butane. Butane have this carbon skeleton, while methyl propane is going to have this carbon skeleton. But now you need to visualize the fact that butane is going to have a higher boiling point compared to methyl propane, and this is because the branching reduces the van der Waals forces in organic molecules. So now there's another form of isomerism that they have forgotten in this point, and this isomerism is called tautomerism. And now, what is tautomerism? Tautomerism is a form of isomerism that exists in order for the transition of functional group. Example: there's a tautomerism between a propanol, a tautomerism between propanol and and propanol. So this is another tautomerism where the double bond is going to produce a CO, a carbonyl functional group on the next molecule. So this is a propanol. This is a tautomerism. So a tautomerism is going to exist between an enol and then an enol, and then the other one is going to be a carbonyl group. So these are the different things involved here. The last one is going to be stereoisomerism. So now, what is stereoisomerism? I've already defined stereoisomerism. So now let's visualize the types of stereoisomerism. We have two main types here. We have the first one, which is a cis-trans isomerism, which is also called geometrical isomerism, and then we have optical isomerism. So what is a cis-trans or geometrical isomerism? Again, you have atoms having the same molecular formula but different spatial orientation of certain groups around the molecule. So example, this is a cis form, and this is a trans form of bromoethane. So bromoethane, when you have the molecule, the same group of molecule on the same side, same group of atom or same group of functional group on the same side of the molecule, that is going to be called a cis isomer. But when it's going to be diagonally oriented as such, it's going to be called a trans isomer. So now let's visualize the next one, optical isomerism. So in case of optical isomerism, we need to know that this is the existence of atom having the same molecular formula but different ability to rotate plane polarized light. So now, and this different ability to rotate plane polarized light can be due to two main reasons, and due to one main reason, that is a chiral center. And the chiral center is mostly a chiral or an asymmetrical carbon atom. It can also be due to another reason, that is due to the superimposible law. So the superimposible law states that if you cannot find the asymmetric carbon atom, you try to divide the bond toward the middle and find if the molecule is going to be superimposible on the other. So now this is going to be seen here. You have the asymmetric carbon atom, and here you can have the three-dimensional view, the zigzag model that I've initially spoken about, or the cram model. And when you place it in front of a mirror, you realize that this molecule is going to be dextro-rotation molecule. Here is going to be in front of the mirror, and this H is going to be behind the mirror. This OH is on the plane. These two are going to be on the plane of the mirror. But this one is going to be in front of the mirror. This one is going to be behind of mirror. So now this other molecule is going to be found when you have the mirror image, but you need to know that one, the mirror image is not this actual image. So this mirror image is the L form, and this one is going to be the D form. So this one is dextro-rotatory and this one is levo-rotatory, the L form. This is the D form and the L form. And now usually the L form, which is levo-rotatory, rotating polarized light to the left, and the D form, which is dextro-rotatory, rotating polarized light to the right. So now we have certain definitions like enantiomers. Enantiomers are just isomers, optical isomers that have the ability to rotate plane polarized light. And now we also have a racemic mixture, which is made up of an equimolar. It is an equimolar mixture of the two different types of enantiomers. Since it contains the two different types of enantiomer in an equimolar fashion, you need to know that one, a racemic mixture does not rotate plane polarized light, because the two molecules which are levo and dextro-rotation are going to rotate plane polarized light equivalently in opposite direction. Thus a racemic mixture usually do not rotate plane polarized light. So now let's see the other one. We have organic reaction mechanism. So this is the other concept subsection, organic reaction mechanism. So the organic reaction mechanism, we have two main types of organic reactions, which are homolytic fission and we have heterolytic fission. So what is homolytic fission? Homolytic fission is going to be the breakdown of the molecule. We have the breakdown of molecule producing with an equivalent loss of electron to the both molecule. Example, this hydrochloric. So equivalent release of electron here and electron here. So this is a homolytic fission. And in this homolytic fission, it can occur in case of UV. So we have an initiation step. An initiation step first occur when one of these molecules is going to cause another molecule to have another homolytic fission. It's going to cause one of these molecules is going to cause another molecule to do another fission, and that other molecule, or those other molecules which are going to be formed due to this first due to this initial molecule are going to progress in the propagation step, and then the termination step we are going to have addition, the respective additions of the different molecule to produce the final step molecule. So now let's visualize what is heterolytic fission. In heterolytic fission, you have the splitting, uneven breaking of the covalent bond, and in this case you have this one, when it breaks it goes with all the electron, and this chlorine usually goes with all the electron because it is more electronegative. As we have initially defined in the previous tutorial, we said electronegativity was the ability of an atom to attract electron to itself or when it is in covalent bonding. So this is what we have said. So now we need to know certain very good principle in order to know the other types inside heterolytic fission. Inside heterolytic fission, we have addition reaction, we have elimination reaction, we have substitution reaction. And now this addition, elimination, substitution reaction are going to be taking place with respect to a carbon center. And now we need to know that there exist three main types of carbon center. We have a primary carbocation, we have a secondary carbocation, and we have a tertiary carbocation. This primary carbocation is going to be least stable. So when you have a reaction that is going to form a primary carbocation, that reaction is going to take place in a bimolecular fashion. So that reaction is going to take place in a bimolecular fashion. Any reaction, because this is least stable, so another molecule is going to bind to this before rendering it stable, and then it's going to break down to produce now the molecule at the end of the reaction. So this secondary carbocation and tertiary carbocation are slightly more stable compared to the least stable reaction, and this one are going to progress while is there a unimolecular fashion. Example, we are going to have elimination and substitution unimolecular are going to progress when you have secondary and tertiary carbocation, while substitution and elimination, substitution reaction are going to take place with substitution bimolecular are going to take place with primary carbocations. So, and this stability comes, and the reason of this stability comes because of the alkyl group. There's only one alkyl group that's attached here, so you can only give one alkyl group is only going to give one electron to this carbon to stabilize it. But here you have two and you have three alkyl group you are going to stabilize this molecule. And this is the same reason why you have Markov-Nikola stabilization principle in cases of binding of an alkene molecule with an asymmetrical molecule. So now let's visualize addition reaction. In addition reaction, you have the binding of a certain molecule to an electron-rich center. So in this case, you have an ethene. We have ethene molecule binding to that. It's going to be electron-rich. So you have elimination reaction. You have the binding of. You have a substitution. You have instead a loss of certain groups of molecules. Example, you have alcohol in presence of concentrated sulfuric acid at 180 degrees is going to cause elimination at C2H4 to produce this molecule. And then we have substitution reaction. Substitution reaction, usually this is the first step which occurs via a homolytic fission, and now the next step we have hydrolysis. So in this hydrolysis, what occurs in this hydrolysis? So when you have the hydrolysis of the haloalkanes, the first thing is that you can have substitution. This molecule here is going to have only one alkyl group bounded to this molecule, so it's going to progress via substitution bimolecular because it's going to form a primary carbocation with a release of bromide. So now we have seen everything involved here. We have reduction and all that. So from here we can say this is the end of the chapter, and please don't forget to like and subscribe for science video makers. Thank you.